Hi everyone, this is a short virtual course on how to get started with fog computing using the COSCO framework. This is the second video of the 6-part course where we discuss the implementation details of the COSCO framework and the various modules and features provided by them. To implement the COSCO framework, we use an object-oriented programming model and realize it using the Python programming language. I will now provide details of various Python classes which together consolidate to the complete framework. The hosts are created or simulated using the data center class, which provides a list of host objects to the simulator or framework. This class runs the Ansible scripts to configure hosts in the case of a physical deployment and creates instances of the host class. The workloads are generated by the workload class. These are either time series models of IPS, RAM, disk, and bandwidth consumption in the case of simulation, or are actual application programs in the case of physical experiments. The application programs are realized via Docker containers. Next, we have the scheduler class that allows taking scheduling decisions in the form of task selection, which is the get selection function, and task placement, which is the get placement function. Task selection function selects the containers that need to be migrated to another host, and task placement function returns the target host for each task selected by the get selection function. Task placement also selects the target hosts for the new tasks that are generated in that interval. Next, we have the host class, which monitors and manages the simulated or physical hosts. An object of the host class maintains the resource utilization characteristics, such as the instructions per second, IPS, RAM, disk, network, and power consumption. In a physical setup, we get the utilization metrics from running the perfstat command. However, in a simulated setup, we maintain models for IPS, RAM, disk, and network for each simulated host machine. To get the power consumption of the host, instead of measuring the power intake, we use the power consumption model, which gives us the power consumption estimate as a function of the CPU utilization percentage of the host machine. Next, we have the task class, which manages task or container under execution. It is an identifier object that monitors the utilization metrics, again like IPS, RAM, disk, and ID of the host at which it is running at the moment. Also other things like creation interval, interval at which it starts execution, interval at which it ends execution, the complete execution time, and the migration time. To do this, we have two main functions: the alloc execute function, which allocates a new task to the input host, the migrate function, which migrates a running task to another host machine. The migration time is calculated as the RAM size divided by the amortized bandwidth between the source and target hosts. In alloc execute, if the task placement is not possible, it is added to a wait queue. For the framework, we have two more classes, the server and the agent class. The server class resides at the fog broker and sends decisions like allocation, migration, and getting resource metrics as HTTP requests to the agent. The agent class executes at the fog worker and runs a Flask service, taking inputs from the server and sending back the required data for executing the ordered commands. Then we have the framework class that contains all the implementation of the physical container management, with also monitoring of the hosts and containers. It also determines if container placement is possible. It checkpoints, migrates, restores containers, and destroys completed containers. This is the umbrella class, which when we run the execution on a physical platform, having the pointers to all the hosts, tasks, schedulers, and the underpinning simulator object. It also checks if the placement of a task is possible by checking whether the target host would be overloaded when the allocation or migration decision is executed. The next is the simulator class, which provides the same function in the case we execute a simulated setup. Finally, we have an auxiliary class called the stats class that maintains logs of utilization metrics of hosts and workloads, QoS scores like total energy consumption in each interval, workload queue lengths, and so on. So let me now discuss the code implementation of the COSCO framework. All the code is available open source as part of a GitHub repository, the link to which is available in the description. As you can see, different folders contain the code implementation of different classes that we just discussed, and all of them are bound together in the main.py, which is the entry point of this particular code. The GitHub repository also provides a brief README where it gives a basic background of the work itself and also a quick start guide. We also provide a wiki, which is the code documentation of the tutorial that we'll be discussing right now. So the implementation details, installation and environment setup instructions, and also the instructions to run the experiments. I've currently cloned this particular repository in my local machine. So as you can see on the left, I have the repository files, as well as on the right, I've opened the main.py entry point of this code. So initially there are different imports. We import the different modules like the framework class, simulator class, different schedulers, the stats module, and so on. To use this particular main.py file, the entry point, we call it using as follows. So we run python main.py -e, we specify the environment. If the environment string is empty, then we run it on a simulator. If it is either of AWS, OpenStack, Azure, VLAN, or Vagrant, we run the corresponding environment. For this particular course, I'll be running on a VLAN environment, which is pre-deployed virtual machines on an Azure platform, but being executed as part of a IP HTTP REST API communication platform. Then -m, we provide the mode. Mode 0 means we want to create and destroy the VMs. Mode 1 means that we want to only create the VMs. Mode 2 means that we do not want to create or destroy, we only want to execute the different applications. And mode 3 is when we want to execute and destroy the VMs that have been created. And typically what happens is that first we would use mode 1 to create the VMs. This would deploy or install the required packages in the fog worker environments, and then we run in mode 2 when we want to run experiments, and then we want to run mode 3, which uninstalls all the files that were deployed at the time of installation in mode 1. The mode is only relevant when we use the environment other than the simulator. Otherwise, this mode is not used. Then there are some global constants. Some important constants include the number of simulation steps. This includes the information of how many scheduling intervals we want to execute in our experiment. And we also have the interval time in seconds. So currently it is set to 300 seconds or 5 minutes. So each scheduling interval would be executed at a length of 5 minutes each. And this is fixed in the whole experiment. Then we also have the number of host instances that we want based on whether it is a simulation platform or a physical setup. We can define the number of hosts that we want in our setup, and the number of containers. So containers is the maximum number of tasks that can be executed at a time. This can be set to the number of hosts itself, or we can specify it as a multiplier of the number of hosts. Then we also have some maximum limits, like total power is 1000 kilowatts, router bandwidth in terms of megabytes per second, number of new containers as a Poisson distribution, the mu of that lambda of that Poisson distribution, and also some other auxiliary information. The first function that we have here is the initialize environment. What it does is that it initializes a database. This database class is actually a placeholder for the InfluxDB database object that runs on the fog broker, and it maintains all the utilization metrics, especially for visualization purposes. Then we have this initialization of the data center, as we just discussed. So based on whether it is a simulated or a physical setup platform, we can create a simulated environment, or we can also create a physical data center. Then we initialize the workload. For example, we can initialize the defog workload applications that are used in the paper for the physical setup, or the BitBrain workloads in our simulated setup. Then we initialize the scheduler. Then we initialize we generate hosts. So let me go into the details of this in a bit. And finally, we initialize the framework or the simulator objects. And finally, the starts file, or starts object that we want to create to measure or create logs of the resource utilization metrics. And the rest of the implementation is fairly straightforward. We create workloads, we check, we deploy these workloads on the environment. We get the placement decision for these new workloads, because in the initial or the first step, we do not need to have any selection policy. So we only create a placement decision. We migrate these particular, or allocate these particular tasks to their respective hosts based on the decision. And finally, we update the workload characteristics based on which particular tasks were deployed. And then we also save stats. After this, things are mostly repetitive. So after the first initializations, we don't need to initialize things again. So we only have a step simulation function. Again, it is fairly straightforward. We create new containers or new tasks. We deploy these particular new tasks in our environment based on which particular container buckets we have. So what happens here is based on the limit that we specified of the number of containers, we only deploy those containers that does not exceed this particular limit in first out fashion. Then we run a selection policy. We select the active hosts or active tasks from those hosts that we want to migrate. Then we have a decision, which is both for the selected tasks as well as for the new tasks. So the selected task and those tasks that were deployed. And once we have a decision, we filter that decision based on that we do not have a decision that is redundant. For example, if I want to migrate a container that is already there in a particular host, then that particular decision is redundant. So I filter that decision. And finally, I run the execute that particular decision in the environment and update my workloads. So this is what happens in every simulation step. And let me now go into details of how these different functions work. So the first and foremost, I'll go through these implementations via the placeholder implementations in the simulator class, just for simplicity. For the framework, things are very similar, although the only change is that rather than running through or executing these different functions in the fog broker itself, where we are running the code, it executes it on a worker node using HTTP REST communication. So the simulator class is defined as follows. We have various variables like the host list, container list, the interval time, and so on. We also have other parameters like scheduler and total power, total bandwidth that we defined in our environment in the main.py. Then we have some other functions like add initial hosts, add initial containers. But these are only run in the first simulation step. Then we also have add container. This adds the container in one of the 10 buckets. For example, if I have maximum 10 containers, it deploys the container in one of the 10 buckets if possible, or if there is no space available, then it returns the container that could not be deployed. Then we have some other subsidiary functions like get container of host based on the host ID. So this returns all the containers that are present in that host. Then we have get placement possible. This is a very important function. For example, it checks that if I allocate a particular container to a particular host, then would any of these IPS requirement, RAM size requirement, disk size requirement, these be violated or not? If yes, then it will return false. If it is not, if it is not violated and the placement is possible, it will return true. Then we have the initial allocation function, which runs it for the complete decision. And finally, we have the simulation step, which is run at every scheduling interval. And what it does is that it takes a decision based on the decision is actually a list of ordered pairs, which is the container ID and the host ID. So for each container ID and the host ID in the decision, it tries to allocate that particular container to the target host. And if that container execution is completed, for example, if the trace or the CPU utilization has gone to 0, then it destroys that container. Let me now show you the container class. The container class is fairly easy to understand. It has these different metrics like the SLA requirement, RAM model, disk model, the creation interval, the interval at which it started execution, and total execution time and total migration time. The most important part of this particular class object is the allocate and execute. So what happens here is that we first consider whether the host ID is not equal to the target host ID that we have in our allocation decision. If this is the case, then the migration time, we take the migration time from the previous interval, the total migration time, we add the time it takes to transfer that particular container to the target host, which is the container size divided by the bandwidth allocation. And we also add the latency of that particular host machine to the fog broker. So for instance, if both the source and the target host machines are in the same layer, if they are in the same, say for example, both of them are in the edge layer or the cloud layer, then the latency between them is considered 0. Otherwise, it is the latency that is considered is the absolute value between the latency of the cloud layer and the edge layer from the fog broker. So the complete migration time is the time it takes to transfer the container object, as well as the latency of communication between the two layers of these hosts. Then we allocate the host ID to the target host ID, and that is how the migration takes place. The execution is slightly different. What happens here is that we add the total migration time from the allocation part, and the execution time becomes the interval time of the environment minus the migration time. This is because things are happening here in non-blocking fashion. So what happens here is that all the tasks that are being executed, we do not wait for these the migrations to take place to run an execution. So what this entails particularly is that, say for example, if my interval time is 5 minutes and my migration time is say 1 minute, then the execution that would be the time length for which this particular task could execute on that target host would be only 4 minutes. Then the execution time is added to the total execution time of the particular container, and the completed number of instructions are added based on the apparent IPS times the minimum of execution time and the required execution time based on whether the particular container has already completed its execution or not. Another important class object is the host object. This also has the RAM, bandwidth, and disk utilization metrics. So this is also fairly straightforward. We have not just the utilization metrics, we also have the capacities. So we have IPS capacity, RAM capacity, disk capacity, bandwidth capacity, and so on. And latency is the latency corresponding to the communication between this particular host and the fork broker. And also we have the power model. Power model is, as I just discussed, power model allows you to get the power consumption estimate based on the CPU utilization of that particular host. So the power model might be something like this. Say, for example, if I consider a Raspberry Pi, then I will have a list of power consumption in, say, watts, and this would be the power consumption, say 0.45 watts at 0% CPU utilization and 1.75 watts at 100% CPU utilization. And for any CPU utilization in between, we can do linear interpolation to get the power consumption. These values can be received or downloaded from the spec benchmark repository. Some of these, for example, the Xeon X5570, which are used in the Azure platform, can be seen in this particular page. So we have the target load as well as the average active power available or consumed by that host machine. And yes, so these are the different functions in the host class object, which provide the different utilization metrics as well as the available metrics. For example, the capacity minus the utilization consumption of IPS, just to make sure that we are not exceeding the capacities, and these available resource utilization never goes less than 0. For the framework, things are fairly similar. The only difference here is that as the simulator is an event-based simulator, so we don't actually need to wait for the execution or the complete migration to take place, or even the tasks to run in an actual system. So the only difference in between simulator and framework part is the sleep command. So this actually runs the sleep command for that particular interval time. So for example, if it is a 5-minute interval, then it will sleep for 5 minutes. The broker will sleep for 5 minutes minus the amount it took for calculating the scheduling decision. And another slight difference between the framework and the simulator is that in the framework we have the server and the agent class. The server has this HTTP request handler. What it does is that whenever we want to create, destroy, or get host statistics like the utilization metrics, it creates a HTTP request and sends it to the target agent machine. For example, other commands like checkpointing, migrating, restore, all of these commands are sent via HTTP requests, and the corresponding commands are executed by the agent node. So the agent node receives that corresponding opcode, and based on which opcode it received, it performs that specific function. For example, if I want to checkpoint a particular container that is running in that host machine, then it will call the checkpoint node. It will run the sudo docker checkpoint create CRIU utility, and when I want to migrate, it will create a tar file in the temp folder and migrate or SCP that checkpoint to the target host. When I want to restore, then it will create a particular container, and it will run that particular container using the particular checkpoint file that was transferred using the sudo cp command in the migrate function. So that checkpoint and migrate functions are run in the source host, and the restore function are run in the target host. Finally, we have the stats object. This maintains the utilization metrics, the workload characteristics, the scheduler characteristics and other things like QoS parameters and the waiting length or the length of the waiting queue and so on. So at the end of every interval, we call we call uh, we call the save stats functions. What it does is that it saves the host information, workload information, container information, um, the container information that are active and the container information that was from the start, the 0th interval. It also saves the metrics. So let me show you how metrics are saved here. Energy is like it saves the energy for each host times, which is like power times the interval time. The energy, total energy is the sum of all the energy consumptions. Then energy per container interval is the sum of the energy divided by the number of active containers in that interval, and so on. Similarly, we can calculate the response time, which is the total execution time and total migration time. Then we have like migration time, which is the sum of migration times of each of the containers. And SLA violation is the length of this list where the destroy at, which is the interval at which it was destroyed, is more than the SLA deadline of that particular container. And wait time is the interval at which it started execution minus the interval that it was created at, this particular workload or container. And similarly, we have these different utilization metrics for the containers and the host machines. Then another very important part that the stats object does is it runs a simple co-simulation loop that we will be using very soon. The simple co-simulation loop, it does things as follows. So it takes a decision and it executes a single step simulation using some of the assumptions that we have. So a simple simulation does not run any LSTM model. It only takes the existing host and container characteristics and just takes a single step simulation given the particular decision and tries to return the energy and response time estimates for the next interval. Thank you for your kind attention. Do make sure to check out our paper, the link of which is in the description. For any queries, please feel free to send me an email. See you in the next one. Cheers.